Good morning, Professor Yang and ladies and gentlemen. Thank you for coming to this pair distinguished lecture. Today we are very happy to have Professor Liu Bin, who is also the Deputy President for Research and Technology from National University of Singapore, as our distinguished speaker. So I will also like to welcome all of the participants online. I know that we have normally over 10,000 people participate online. I appreciate your participation. And now I would like to invite our Vice President for Students and Global Engagement, Professor Ben Yan, to introduce our speaker. Professor Yan, please.
Thanks, Prof Chen. Professor Ben Liu, distinguished guests, colleagues, and friends, good morning. It is a great pleasure to welcome you all to this distinguished lecture organized by the Prof LIU Academy for Interdisciplinary Research, in short, PAIR. The PAIR Distinguished Lecture Series is a flagship initiative that Prof LIU PAIRs has been running for years, consistently bringing together leading scholars and innovators to share ideas with us and also those online. Today, we are privileged to host Professor Ben Liu, Deputy President, Research and Technologies, and Tan Chin Tuan, Centennial Professors at the National Universities of Singapore, NUS. At NUS, interdisciplinary research is a strategic priority. Over the years, NUS has invested significantly in building its interdisciplinary capacities, establishing research clusters in areas including health innovations, sustainability and urban solutions, smart nations and materials research. Among them, the Smart Nation Research Clusters has grown to include over 15 centers and institutes driving impactful research and innovations. At Prof LIU, interdisciplinary research is at the heart of the university's strategic visions, guided by the United Nations Sustainable Development Goals. Prof LIU PAIRS is committed to developing and delivering practical, scalable, and impactful solutions to pressing global challenges. PAIRS currently comprises 20 research units at the university's level, organized under 3 major themes: advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. Through research at these 20 units, as well as initiatives that fosters collaborations, nurtures young talent, and engage external partners, we strive to establish PAIR as a leading hub for innovations and meaningful global engagement. Allow me to share some of our recent achievements. In the past years, PAIRs secured over 615 million in external research grants and donations, received over 260 awards and recognitions, produced over 1,800 publications, and obtained over 30 patents. To amplify their research impact further, PAIRs actively pursues international collaborations, fostering external partnerships that deepen our contributions to addressing global challenges. With both Prof LIU and NUS demonstrating strong commitment to interdisciplinary research and cultivating robust ecosystems, I'm confident that the two universities can leveraging complementary strengths and join forces to co-create transformative solutions. I'm certain that Prof LIU's presentations today will offer valuable insights and inspirations that pave the way for deeper collaboration. Last but not least, I would like to thank Prof LIU for enlightening us with her wisdom, and all of you for being here today, and also those online. I trust you will enjoy Prof LIU's lecture. Thank you.
All right, good morning, everyone. It's really my great pleasure to be here. I actually spent 2 days to review PAIR. It was such a wonderful time that I see how the impact has been made by PAIR over the past 4 to 5 years in bringing the different people and different departments, and more importantly, different disciplines together to foster this interdisciplinary research for Poly U. And of equal importance, as of today, PAIR has grown into a global brand. No matter whether we talk about it in Singapore, in the US, or in Europe, people are aware of this brand that is from Poly U. So it's very important for us to carry this forward and make sure that everything we do would actually bring Poly U to the next level of excellence. All right, so today I'm going to share with you something quite special. It is what we learned from a mistake that is made in the laboratory. And I would like to share with you how by now, when AI is so popular, and when we review all the literature and we learn things from online, how much care that we should pay in order to make sure that we really learn the right and correct knowledge and carry the knowledge forward. So what I want to share with you is the isostructure doping for ultralong organic phosphorescence. So I work on the organic molecules, and I'm specifically interested in how to bring the organic molecules into the aqueous media. And I trust that many of you are working in the materials domain, and you can classify yourself broadly into I'm working on organic materials, I'm working on inorganic materials, and there's a lot of competition. So 20 years ago, when I was a student, I decided that I would do something slightly different. I don't care too much about the composition of the materials, but I care a lot more is how can I bring the materials that everybody is studying under the normal condition into the aqueous media. And as a consequence, we can use these molecules for biomedical applications, and we can use those molecules for multi-layer electronic device. And as I go along, I realized that there was a core issue. The issue is if we want to bring organic molecules into the aqueous media, they often aggregate. And as a consequence, they will lose their optical feature. And in order to solve that problem, we spent literally about 10 years' time to develop the molecules with aggregation-induced emission that we capture the nature of the molecule that they like to aggregate in the aqueous media so that we can amplify the optical feature as much as we can. And along this line, we find something really unusual, right? So what we wanted to solve was a problem that when we do the biological imaging, there's a lot of background signal, which is the autofluorescence or bioluminescence. What we wanted to do is to introduce organic molecules with high brightness, but more importantly, long lifetime, so that we will be able to play in a way that will eliminate the background signal. So as we go that direction, we find something really unexpected, and that forms the foundation of the story that I want to share with you today. Now, when we talk about phosphorescence, basically, we are emphasizing on one of the key steps, which is the intersystem crossing and phosphorescence. When we look at this, we have to overcome at least 2 critical issues. The first is the poor efficiency of the intersystem crossing because it's a process involves the transition from singlet state and triplet state that is spin forbidden. So this process is naturally not very efficient. And the second step is the phosphorescence process. And we understand that it's very difficult to observe the room temperature phosphorescence because even we have sufficient triplet state, they may not go back to the ground state via radiative decay, then we will not be able to capture the phosphorescence, right? Now, if you imagine that we want to bring this phosphorescence into biological application, we have to overcome additional barriers, which are the presence of water and the oxygen. So all this will actually quench the triplet state. So as a consequence, it's very difficult to achieve. So for many years, people don't believe that phosphorescent molecules can be brought into aqueous media for biological applications. Now, in 2019, we actually discovered a method that will allow us to manipulate the organic molecules into either amorphous nanoparticles or simple organic crystals. And once we're able to differentiate the molecular aggregates into amorphous or the crystallized state, we're able to conduct the cell experiments and later on the animal experiments. So what we observed here was that in terms of the background signal, if the molecules is in the amorphous state, they're not able to show the phosphorescence at room temperature in the aqueous media, so that you don't see background signal, you also don't see any real signal from the molecule. So as a consequence, you will see very bright fluorescence at the background from the animal by itself. Now, if we're able to make the molecules into the small nanocrystals, then we will be able to have the cell imaging with extremely low background signal because they're captured at a different lifetime frame. And more importantly, now we really don't have any background signal from the animal so that we can differentiate the signal of interest from the background. So with this initial success, we just asked ourselves, what can we do to make the phosphorescent nanocrystals much brighter? So the first step, very simple, we went to the literature to see which molecule actually shows the phosphorescent emission so that we can synthesize them and make them into the particles. So we searched the literature and we find one interesting article. So that reports a carbazole-based green phosphorescent molecule. So I asked my postdoc to synthesize that molecule, which is a very simple structure. You have a carbazole and then a benzene and then a carbonyl group. So it's a 2-3-step synthesis for the organic molecule. What we discovered was that if we synthesize the molecule would show the reported phosphorescence phenomenon. But if we purify the molecule, because when we do the biological experiment, we want our molecules to be as pure as possible. And then after a few rounds of purification, surprisingly, the phosphorescence signal disappeared. So our initial thought was the compound was not stable. But if we look at this compound, it's like very stable, right? So that triggered us to understand exactly what went wrong so that this phenomenon can disappear through the purification process. So we decided to synthesize the raw materials in the laboratory instead of getting them from the market. All right. So what we find out is if we use lab synthesized carbazole to start with, we're not able to actually observe the reported phosphorescence. And we tried for other examples. Again, if we use commercial molecules as these starting materials, we will be able to reproduce the phenomenon in the literature. But if we use pure compound to start with, we will not be able to reproduce that signal. All right, and then we did detailed analysis of the single crystal structure and everything. So with the impurity and without the impurity, there's no difference in the crystal structure because the amount of impurity is extremely small in this case. We were surprised, but it's very difficult for us to convince the community that there are mistakes in the literature, and particularly for the high record molecules for room temperature phosphorescence. So we spent a lot of time looking into other molecules of great promise that have been reported in the literature. As you can see from here, these are all great papers in top journals. And each paper is reporting one of these molecules or the combination of them. It's very interesting that all these molecules, if you resynthesize them from pure laboratory molecules, you will not be able to reproduce the phenomenon reported in the literature. That's a clear indication those phenomena observed has nothing to do with the chemical structure in terms of the structure, property, functionality. All right. Instead, there are mysterious molecules that coexist into these structures that has transformed their optical properties. So it took us a long time to repeat these experiments because it took a lot of courage to tell people that what they published actually was not right. Now, let me use carbazole, the initial original material, as an example. All right. So we can get these molecules from a lot of commercial sources, and we can also synthesize them from the laboratory. So the key difference is the phosphorescence phenomenon. If it's from commercial sources, you will be able to see this bright yellow emission after the light illumination is removed. But if we get the pure molecule, this phenomenon disappears. And a lot of us often use HPLC to purify the compound and show the HPLC trace as the indication of purity. What I want to share with you here is for these molecules, depends on the solvent combination and how quickly or how slowly you run the HPLC, you will get results that are extremely confusing, that you thought that they're pure, but they're not pure just because you did not find the right condition to run the HPLC. All right, so it took us about 3 years' time to isolate this isomer from the carbazole, partially because they're isomers. And this molecule is also not very stable in solvents, in the presence of oxygen, etc. So we got them, we lost them, we got them, we lost them. It took us a long, long time. So eventually find out that there is a small amount of the BD, which is the isomer, that coexist in the commercial carbazole. And when you add even 0.1% of BD into the original compound, you will be able to regenerate the phenomenon reported in the literature. So that's one of the evidence to indicate it is not the original chemical, but rather this 0.1% to 0.5% of the isomer that coexist with the original compound that give you all the observed phenomenon. All right, so the extreme case can be demonstrated here. If you look at the carbazole itself or the BD in the solid state, so they didn't show any obvious fluorescence or phosphorescent signal. Now, if you mix a very small amount of the BD into the CZ, right? Now it's kind of like an alloy, but it's a small amount of dopants of BD incorporate into the CZ and grow a crystal. And amazingly, you will see that a new peak actually emerges with the increased concentration of the dopants. And then it will decrease because of the triplet state aggregation that is at a much higher concentration that will quench the phosphorescence. Now, recently, we built a very special setup which will allow us to capture extremely low optical signal. So in this case, we're able to observe that the pure original study material actually shows a very weak luminescence. And once we disperse this dopants into this powder, right, and then we see literally almost 10 to 100 times amplification in the phosphorus region. But of equal importance is if we are doping this molecule into the polystyrene at the platform. So that means we're actually disperse the dopants into the polystyrene, right? We will also be able to get a very high phosphorescence. So that's an important experiment to show to us we're not able to capture the optical signal. That's not because they don't show room temperature phosphorescence. It's only because we are not able to create the environment to make sure that we're able to induce the light emission as reflect by the molecule itself. So it took us another 3 years, and hopefully in a month or two, you will see this new paper about the mechanism. So even the two molecules are just simply mixed together. There's a complicated mechanism behind. So long story short, so if we look at the mixture, right, so we have these host molecules and very small amount of dopants. And upon light illumination, we will have the singly excited states and a small amount of the charge separate state. But because the dopant number is very small, and as a consequence, you can imagine the number of the charges formed in the charge separate state is very minimum. All right. And along the next step, the excited state can go back to give fluorescence. That's one pathway. And then the triplet state can also undergo the energy transfer to the gas molecules. Then you will observe the phosphorescent emission from the gas. And the rest part of the triplet state from the host, they may also go down by themselves so that you are expecting the room temperature phosphorescence from the host. And depends on the energy levels between the host and guest so that you may only be able to observe phosphorescent emission from the guest, and you may be able to obtain both from the guest and the host. Now, after that, at a different time scale, this charge separate state, they can migrate and recombine, and this will give you the persistent luminescence. So you will have different signals at different time with different brightness that captures the time frame and the light emission of the system. Now, if we look into the literature, or if you look into our common practice, this problem is not casual. All the commercial available for carbazole actually has this impurity. And this diagram actually shows how the commercial carbazole molecule is produced. It actually through the core and then distillation and refinement, and then you get commercial carbazole with purity from 95% to 99.99 whatever percent. But nonetheless, for many of these molecules that are commercially available, we will be able to identify this isomer as one of the impurities, not all, right? Now, if we further quantify the presence of the small fraction of the impurity, you will find out that even in the very, very small amount, but its impact is very big. So in terms of the emission, with a small amount of the impurities, that this whole group is actually the commercial available carbazole that gives you the emission, right? And then this one is the purified one. So the difference is literally 54 nanometer. And we can also quantify how much or what's the percentage of the impurity. And it's very small amount of the impurity that exists in carbazole actually varies from 0.1% to 0.5%. So that is why if we rely on NMR to check the purity of the compound, we're not able to detect this small amount of the impurities. And that is the reason for so many years, people are working on this compound, but no one was able to discover that there's this small amount of impurity that is making a huge difference. And this impurity is very difficult to separate. So if we use traditional column recrystallization, we will not be able to easily get rid of this impurity, but instead we can get rid of other impurities so that the doping effect becomes even much more obvious. So that explains why there are so many groups are working on this compound, but nobody actually was able to discover that there's this tiny impurity that is the real reason to explain this property. Initially, we thought this is just a small incident. And when we look into the literature, and we find out this is not a small problem. This is a problem for over a century. Since nearly 100 years ago, people were discussing what is a phenomenon. So all this light emission, sometimes they exist, sometimes they cannot reproduce. And then in between, there are debates whether this is because of impurity and this is not impurity. But fine, we're very lucky. We're the first one to discover the impurity and explain how this small amount of the impurity actually is making a huge difference. Now, it happens that carbazole, and many examples I will share with you later on, happen to be one of the most important building blocks for organic electronic materials. Even over the past 10 years, there's literally 20,000 papers that uses the commercial carbazole to synthesize all different kinds of compounds. And I'm pretty sure all those compounds, more or less, have small amount of impurities that are contributing significantly to their optical properties. I cannot guarantee that all the phenomena that are affected by the impurity, but I'm pretty sure all of them contain the impurity that is worth pursuing, especially when we separate into big blocks of energy, catalysis, and optical features. So we're working on that. It's going to take a long, long time for us to be able to share with you the next big discovery. But nonetheless, our job is not to identify impurities and separate them. Our job is more important. So what can we learn from the impurity? And in order to answer that, we need to know where does the impurity come from. Initially, we thought only relevant to carbazole, and it's from the study material. But as we study more, And the community is more interested in this phenomenon. And then we find out this problem is much, much bigger, because in addition to the materials to start with, there are side reactions. And side reactions happens all the time. And that's why we're not going to get 100% reaction yield or the 100% selectivity for reactions, right? And then there are also a lot of unknown species and unknown reactions or systems that remain to be explored. So I will quickly go through some of these systems. And I'm pretty sure if you are working in the materials or chemistry, you are familiar with these systems. And I just want to remind you to be cautious. This is something you didn't pay attention, but this is something probably is going to change the properties of the system that you work with. So the first system is the triphenol, is the carbazole-based system. So in addition to the molecule we isolate, there's another research group that actually isolate this molecule from the starting material. So this small amount of impurities contributes exactly the same phenomenon. It can also dope the original materials that it gives you the observed phosphorescence, which is not from carbazole itself, but rather than from these dopants. So similar to carbazole, there are other important building blocks for organic electronic materials. So two of them I highlight here, the DPD, which is the dialphine at the center, and DBF. So these molecules are used to synthesize a lot of organic functional materials, and they have different impurities, and this can be two of them. And as a consequence, you will be able to find out, again, for these molecules, if you purify them very carefully, you will not show optical properties as phosphorescence. But if you just randomly get them from commercial resources, you will actually face the problem as I shared with you just now. Now, in addition to carbazole, there's another big type of molecules, which is triphenol-amine. And if you're working on organic electronics, you're working on solar cells, and you're working on many, many dye molecules, you cannot bypass triphenol-amine because one of the very popular electron donating group. So for this molecule, be careful. More or less in the starting material, you will have these impurities that are mixed together. And a lot of the phosphorescence you observe is not because of triphenol-amine itself, but rather than because of the coexistence of this kind of impurity from the beginning. All right. So in addition to the starting material, the even scary side is the impurity from the side reaction, because almost every reaction has a side reaction to go along, right? So in this case, it is the solvent. So whether you use ethanol or use DMF as a solvent would actually affect whether your final product will end up with the bromide or end up with the dimethylamine. So bromide actually react with the DMF to give you dimethylamine. Yeah, so these two molecules, a small fraction of the X coexist, will give you the phosphorescence. If you don't have this impurity molecules, or if you don't use DMF as a solvent, you will not be able to create this undesirable or desirable phosphorescence signal. All right, so that tells you solvent actually is critically important. The same is also true. This is a more complicated example, but again, it also shows that when you use DMF as a solvent, you can trigger side reaction, which will serve as the intermediate, and as a consequence, you are even able to form a more complicated ring structure that offers you the phosphorescence not belonging to your original compound. Now, recently, we also find out that for the series of molecules showing here, they are also not producing the phosphorescence reported in the literature, but instead, a small fraction of the dopants is able to induce very bright phosphorescence. Now, in addition to that, for the triphenol-amine-based system, right, it can easily undergo this Suzuki coupling, especially when we are using the molecule to produce the borate and the borate coupling with the bromide to give you the side product, right? So the small molecule here is able to completely enhance your phosphorescence. If you don't have this side product, your phosphorescence will be very low or almost eligible. All right. So similarly, we can also isolate other impurities from the same reaction that is the reason contributes to the phosphorescence rather than the molecular structure as we saw. Now, this slide actually listed other systems that we don't have time to look into, or because their optical features are not so significant to create a record in the system. So there is clear evidence that there is some impurities that coexist with the compound that gives you the observed phosphorescent signal, right? But nobody actually has spent enough time to figure out exactly what is the compound. So this remain to be discovered. So once we understand that starting materials, reactions, and everything can trigger this unusual phenomenon, then the question is, how can we leverage all this to learn the design so that we become more successful in creating room temperature phosphorescent compounds? So what I want to share with you here today is one of the ideas that we have, which is the isostructure doping. So as far as we knew that some of the isomers coexist in the system, will be able to induce the room temperature phosphorescence. Why don't we just leverage that to design isostructures and on purposely inject into the molecules so that we can transform the initial short emission in the phosphorescence range into the potential elongated phosphorescence emission. Now, to do this, let's review this diagram again. So for room temperature phosphorescence, actually, we are pretty much bothered by the poor transition in the system crossing between the singlet state and triplet state because it's spin forbidden. All right. So we ask ourselves, do we need to go through that pathway as we learned over hundreds, thousands of years? Is it possible for us to introduce a small amount of dopants that will be able to create a charge separate state, which will have a different distribution of the singlet state and triplet state, right? If we can compete or bypass the intersystem crossing, we stand a much higher chance to create triplet state that will allow us to have much brighter and longer emission as we desired. So this is one of the design principles that we wanted to introduce. All right, so based on this, we start to design our molecules by looking at the host molecules and trying to find out what are the potential molecules that will be added into the host to actually transform the optical properties. So we have looked into the molecules that are most difficult to achieve, for example, in the long wavelength emission, and also with the relatively longer lifetime that we want to achieve. So in this figure, we summarize those reports in the literature, and then we also input the data points that we create from the lab. And we care a lot more is those red dots on the top right corner. They are in a very long wavelength emission, and they are relatively with long lifetime span, right? So it's very straightforward that if you use isostructure doping as a methodology, you can easily create long wavelength emission with reasonable long lifetime as you wish. So up to now, we're able to create systems that can last hours instead of nanoseconds and picoseconds with the fluorescence for the optical imaging applications. Now, let me give you specific examples of how this phenomenon can be incorporated into anything that we know to change the optical feature just by introducing a small amount of molecule. So the first example I'd like to share with you is mechanoluminescence. So mechanoluminescence is an interesting phenomenon that you press on the certain materials, it will have the charge separation, and then you see either a short duration of the light emission, or you will be able to collect the electrical signal. That's the piezoelectric phenomenon. All right, but what we want to do is to add a very small amount of the dopants into the system so that the materials can maintain initial mechanoluminescence, but we're going to change the luminescence into a much longer duration of emission so that you can capture them with your naked eye for a long period of time. So the molecular design is very simple. Just get any mechanoluminescence system that you work with. But we have to on purposely introduce the isostructure dopants, very small amount, 0.5%, 1% is sufficient. Then we form these crystals, right? as far as you introduce this small molecule, you're going to change the optical feature of the system that you have. All right. So we actually monitor the emission of the mechanoluminescence system after we add in 1% of the dopants. Now we are able to get actually much elongated emission, no longer as the nano-picosecond level. We can easily see them in the seconds level, right? Just by adding this small molecule. And this small molecule is able to change the optical feature is because we leverage on the piezoelectric effect. Whenever the charge separation, we wanted to make sure that exons will be able to land in the charge separate state for the host molecules and also as the gas and host molecules, right? And then we leverage on the charge transfer state to migrate the energy into the gas, and eventually we can collect the long lifetime emission from the gas. All right, just by simply adding small amount of molecules, now we're able to change the optical feature of any system that you may have, and you may want it to elongate emission so that you don't rely on equipment, you can rely on human eye to form the detection. So once we're able to get materials like this, we can actually easily develop into false responsive sensors. And we don't rely on equipment anymore because the light emission as well as the duration is long enough actually for us to capture that with the human eye. All right, so this is one of the first example how small molecule actually can on purpose be designed to transform some of the phenomena that we have in everyday life. So the second example is to really solve the key issue associated with the traditional phosphorescent materials. Many people believe that phosphorescence can only be observed when the molecules is very well defined in the crystalline state, so that all the non-radial decay has been quenched as much as possible, and the light can be amplified as much as possible. But we all understand crystals are not easy to process, and as a consequence, they're not very useful in terms of practical application. So what is needed now is to find a host material so that we can allow phosphorescent molecules to be processable for all different applications. All right, so that drives us to look into the metrics for the phosphorescent molecules. So in this case, I would like to introduce one of the metrics, which is the small molecule. And the small molecule is special. It can form a glassy state. All right, that allows us to process. So we can process these phosphorescent systems with the draw, coil, and forms, right? And what we control here is the temperature-dependent fluid system of the small molecule. Now, this is the molecular structure. It's a very, very simple molecule. But the molecule is specially designed so that it has different conformation, and as a consequence, it cannot be recrystallized very easily. So it will stay at amorphous state for a long period of time. So that will allow us to process the phosphorescent molecule as we wish. Now, literally, whatever molecule that you have, we will be able to find a good host. And you put your fluorescent molecules into that host. When it is very well dispersed, when the non-radial decay is pretty much quenched, we will be able to generate the phosphorescent phenomenon for the molecule that you have or you're interested in. We can significantly enhance the lifetime of the emission for the molecule that you're interested in. All right, so here is just a platform to show that we have a matrix. You put in the fluorescent molecules that you're familiar with, we will be able to give you much, much longer lifetime, not limited to pico-nanoseconds, but into seconds and minutes and even hours. All right, so because we're able to introduce this flexibility into the system, so now you can form the wires, you can form the coils, you can knit, and then you can even have other optical waveguide fibers, etc., all different kind of applications that you wish. So we'll provide a foundation in terms of materials and processability so that you see fit what kind of application you want and what kind of materials that you have, you want it to be modified to have different properties. We can help you achieve that. So the last example actually go back. After we detour for so long, we understand how to select the molecules and how to dope them. The question is, I still want to bring these molecules into aqueous media so that we can use them for biomedical applications. In order to do that, we really hope to form very small structures and preferably crystalline so that they can resist water, resist oxygen in the aqueous media to give us room temperature phosphorescence. So this requires us to develop a strategy to make sure that the molecules can form crystals in the aqueous media, but the crystals will not grow crazy. It has to be confined in the 50 nanometer to 100 nanometer, that range. All right, so we went back to the phase diagram, and I understand nowadays phase diagram is no longer popular among younger generation, but it's so important scientifically that will allow us to find the optimized condition to make nanoparticles, and more importantly, nanoparticles that are crystals. All right, so for any organic molecule that is to be wrapped with block copolymer to form the cold shell or muscle structure, we can actually reference to this phase diagram. And we care a lot about is this ozone region where actually the right solvent and solute combination will allow the block copolymer to form nanoparticles that will wrap the organic molecules at the center. And at the same time, we want to make sure these organic molecules will recrystallize, right? So we also need to look into in which solvent combination that is just good for this molecule to recrystallize concurrently. All right. So if we overlay the recrystallization zone and also the nanoparticle formation zone, so for all the combination in terms of solvent, in terms of the molecular mass ratio, there's only this tiny region. If you operate in this tiny region in terms of concentration and solvent combination, you stand a chance to get the particle. All right. So to elaborate more, so you have to work on two phase diagrams, one for nanoparticle formation, one for crystallization. And you will be able to identify this zone that will give you small sized nanoparticles that are crystals in the aqueous media. And then we can functionalize the surface to make it highly specific for biomedical applications. So we just started this. We haven't really get it complete, but we're happy to share that we are able to offer a bottom-up growth strategy that with very well controlled size and morphology of the doped system and bring them into the aqueous media. Right, so we're able to get very nice room temperature phosphorescence in the aqueous media and with a very well controlled size, about 50 nanometer. So that is not very easy to achieve. All right, so we're in the process of studying the cytotoxicity of these nanoparticles, and we're also evaluating how effectively it is actually able to offer the molecular imaging that is in the absence of the light illumination and in the absence of the autofluorescence. So the initial result is promising, and we're working continuously to demonstrate the biomedical applications. All right. Now, I give you the examples of how we can design the system, how we can process the system for different applications, right? So I don't have time to go through all the applications with you, but I would like to highlight some of the interesting applications that I have in mind and what is ongoing in my laboratory. Now, we live in a world that requires a lot of energy, all right? And then the light on the highway is always on, right, at night. Now imagine if we could have the molecules that shows mechanoluminescence, which means as far as there is traffic across the road, as far as there is friction on the road will be able to offer you the mechanoluminescence. It's transient. As traffic is gone, as the people pass away, actually the road, the materials will recover to the original. So if we can make the lifetime of these molecules to elongate to hours or days, we will be able to reach this in the near future. For the time being, organic molecules cannot achieve this, but for some of the inorganic nanoparticles, the life duration-wise is able to offer that privilege. But more importantly, everything associated with the human behavior and healthcare security actually can be realized with phosphorescent molecules, particularly with our very small dopants that add in existing molecules. We don't need to recreate new molecules. We just dope your existing molecules to give you the optical features. So definitely we can leverage on naked eye to actually detect the optical signal that was previously very difficult to achieve. We can also use chiral dopants into the molecule that you are familiar with. And as a consequence, we can offer you long-time emission and chiral property of the molecule that you can use for chiral sensing. And of equal importance, as we are able to modulate the light emission, which include the color, lifetime duration, and the time-dependent color change, we are able to incorporate all the systems into the optical data encryption that has been ongoing in the lab, and I don't have time to explain to you. All right, in summary, we learned all this from the incident that we did not expect. There are impurities in the chemicals we use, and those impurities are much, much more powerful than we thought. Even 0.1% or 1 part per million will be able to change optical features of the molecules that we work on. So we need to be very cautious because hundreds and hundreds of papers, when they report the so-called structure property relationships, they're not really reflecting the real property of the chemical structures. But instead, there are some very important mysterious compounds that coexist and nobody pay attention. They are the actual trigger that causes all the difference. That reminds us, when we read the literature, we need to be very careful. We always believe that anything written in the books, anything published in good journals are correct. The chances, many of them are not. And many of those papers are actually validated and supported by modeling, by massive other evidence to prove that is the case, which turned out actually is not. All right, so we need to be really, really cautious. It's not I don't trust. This is a great story that I share with my students, that when you look at literature, when you look at the book, you better think rather than believe everything is true and everything correct. That's very dangerous. All right, so now we understand a small amount of molecules can really change a big difference, largely based on the energy transfer and the gas molecules as the deep triplet traps. We will have this paper out in about 2 months' time. If you're interested, please take a look. It took us 3 years. We published all the methodology, all the system we developed in order to understand this mechanism. So it will be very interesting to read that article. Now, in order to make sure the system will be potentially useful and applied, we work on the processability. So we look at the molecular metrics, how we can actually massively deploy a large amount of fluorescent molecules and boost up their phosphorescence emission. And at the same time, we make sure that whatever you need, you want to make particles, you want to do the spin coating, or you want to do the draw to get a fiber, or even very, very big crystals like meter-long crystals for waveguide applications. We have that methodology built for you. All right, I think I would end here. I thank my students, my collaborators, and also funding agency. And I thank you for the opportunity to share with you that science is very exciting and sometimes it's very much unexpected. Thank you.
Okay, so wonderful presentation, I believe. And it is my great pleasure to sit together with my classmate and the former colleagues from AUS. And very happy to see Bing and a wonderful story in chemistry, very beautiful. So we open for the questions. And yes, please.
Hi, Prof LIU. Very nice talk, thank you. And I have 2 questions. And the first one is a very technical one. So why the NMR cannot detect the isomer impurity? So the structure would be very different from the original, the monomer.
Okay, that's a great one. So when I say NMR is not very effective in detecting the isomer, it's not mean that the isomer will not have different features in terms of spectrum in NMR. What I mean is that because the concentration of any impurities in the commercial product is low, you often get 99%, 99.9%, right? We always get 99% or 99% use them without purification. It's by default, we think that's pure enough, right? But actually, because of that small amount, less than 0.5%, NMR cannot detect anymore. NMR is good for anything 95 and below. If it's 95% above purity, NMR is very difficult to find out.
So the technical, your group are using the HPLC, right?
HPLC, I just want to remind everyone to be careful. So we rely on HPLC for purification. In principle, nothing is wrong. But how we can purify them, it really depends on the solvent combination, the speed of eluent, right? If you run very fast, actually 2 peaks can merge into 1, right? So that's why many research papers are now published, the HPLC data to prove this is pure. I'm always very suspicious if the retention time is less than 10 minutes, if the solvent like polarity is like so high. We had that bad experience that for the same compound, same mixture, depend on the solvent combination, we can get you beautiful spectrum, but they're not pure.
Okay, thank you. And my second question is about your hybrid material system using the piezoelectric materials. Actually, I'm working with Professor Liu Wang, and actually my work is really about using the piezoelectric materials to find some mechanical applications.
Yeah.
And I thought that idea was very interesting so I'm curious what kind of the piezoelectric material you use, and is it a single crystal or polycrystal?
We don't mind whether it's single crystal or polycrystal, but we design our molecule or select our molecule to have like high polar. The molecule polar usually have like bromide, azide groups, cyano groups, right? So that as in response to the mechanical force, the charge separation will happen. Right. For most of the piezoelectric, people actually detect the electrical signal, and then their focus is the current flow. But for us, is after the charge separate, how they will be able to recombine and give the emission is our focus.
Yes.
Traditionally, this duration is very short, is pico-nanosecond that level. Now, if we add a small amount of these molecules, we can literally elongate that process to seconds, minutes.
That's very good. And because I'm also using the piezoelectric effect to tune the the semiconducting or optical properties of some materials. And I'm trying to fabricate the hybrid system, and I noticed some very interesting phenomena. The first thing you said, actually the synergy or the synergistic effect is actually depends on how much and what kind of, and also the piezoelectric materials.
Yes.
I mean the single crystal or polycrystal, and many factors would jointly contribute.
Yes.
And another thing is that because you still want to build up your materials, your phosphorus materials on the piezoelectric materials, and you want your materials to be crystalline. And
not really.
Not really.
My goal is to look at any molecule that you may have, for example, right? And what should be the dopants to be designed so that we can add in 0.1% of the molecule, suit your molecule, in order to change the optical properties of your molecule.
Okay, thank you.
Yeah, that's what we want to achieve.
Okay, thank you very much. That's my question.
Can you let us know your name and everybody know who are asking the questions?
Yeah, my name is Kai Wang, and I'm currently a research assistant professor. I just moved from the University of Queensland together with Professor Liu Wang, and we are still working together. And hopefully in the future we have some more opportunities to discuss and collaborate. Thank you.
Good morning,
Yeah,
Professor Liu. This is Leo from FSN. I want to know how far is your technology applicable to the further development in the technology like qPCR or digital PCR, as well as sequencing? Because you mentioned something, I don't know whether it is applicable to the novel development in these two very important techniques in biological sciences. Thank you.
Okay. Well, that's a great question. Your application is very specific, right? So if I'm not wrong, for the sequencing side, the signal connection is not a bottleneck, right? So if the signal connection is not a bottleneck, or the background signal actually can be easily get rid of from the signal that you want to capture for your system, then I seriously don't think that we need to come to this system to give you a much longer lifetime that you can see with your eye. Right? So it's kind of like you're already able to solve all the problems with the current technology. Then this one becomes a bit like abundant. I mean, we can replace your fluorophores with this one, but I don't see additional value in terms of sensitivity or in terms of any selectivity that these molecules can offer, your current molecules cannot. Yeah.
Any other points so we can address together? Yes, please.
And very thankful for your wonderful speech. And I just wonder how far is it from like scale production in industries? Because Professor, you mentioned about these luminance phenomena can only be observed under very strict conditions in laboratories, but in real factories, maybe these conditions are very, rough. And is it applicable in near future?
Okay, thank you. That's an important question for phosphorescence field, right? So for us, because we really care a lot about what kind of the metrics that we can offer so that you can process them, right? So now if we use molecular glass as a metrics, you can literally produce tons of them. And then because you can actually increase the temperature to about 150 degrees C, then you have a fluid, right? And then you can just add your dopants. Then it will naturally mix because it's a liquid and the molecules inside. So process-wise is very much compatible with the industry. But for us, what we're doing now and what we want to achieve is how low we can reduce the temperature so that the processing maybe can be done at 50 degrees C instead of 170 degrees C. That will transition from the crystalline to the amorphous state, right? And how can we make sure that when we reduce this processing temperature, we will hold the final materials in the amorphous state for a long, long time so that they will not recrystallize along the way. So those are the scientific questions that we're addressing now in the lab. But in terms of processability, first, we require very, very small amount of the materials, right? So our goal is very clear. We're not recreating new materials for new functions or properties. What we wanted to do is to transform existing molecules just by adding like 0.1% of the dopants, and we'll change all the properties that you want based on your materials, right? So we work on the processability, we work on the mass production. We want to make sure that your application will not limit it to the crystals currently limited. I don't see any barrier, to make it useful.
The last question is about, you mentioned about many, for nearly 1 century, our phosphate industry was bearing a high impurity. And I want to ask about the safety reasons that will this impurity contained in industrial production will harm our safety because, phosphate is a very dangerous element.
Okay, so that's how the chemistry industry, they draw a lot of raw material from crude oil, and through different steps of processing, cracking, they get different materials, right? So we all study chemistry. We all know all the reactions is not 100% in yield and selectivity. So we get used to the fact that no matter how pure is the compound, no matter how great is the reaction, it's not absolutely 100%, right? We know this, but we just didn't pay attention how big can be the impact of that tiny side products or impurities in the raw materials, right? So I spent a lot of time trying to identify exactly what is the compound so that I can convince people, right? And I think it's something quite alarming and cautious because everybody is using chemicals every day. And maybe a lot of functions are not too much relevant to the impurities, but definitely to the optical properties and to the catalytic reactions that rely on charge separation. or to be more broadly discussed that anything probably associated with the excited state of optically active molecules will be affected by the presence of the impurity. So I see this as something quite important, at least for the chemistry community, in two ways. One is we need to be careful about the materials we use every day, right? And also the reaction conditions. And secondly, because people didn't know this, right? They didn't make mistakes on purpose, but because they didn't know this, and the previous characterization tools are not as precise as now, right? So there are a lot of conclusions made in the literature, unfortunately not right. So we need to be careful about that. So what I'm doing now is really to look into the field and to revisit every examples that set the record efficiency, because I want to make sure those examples will be corrected so that other researchers with better examples and high performance can still claim the high record.
If there's no online question, may I ask one? Yeah. Yeah, thanks a lot, Professor Liu, for the wonderful talk. I think it's a very exciting discovery, and congratulations. So because we are working on inorganic semiconductor, you're working on organic semiconductor. I found there a lot of similarities, like tiny amount of impurity can change the property significantly. But this impurity is also the most important one, because otherwise you don't have the activity there. So my question is more generic. So so in this field, like phosphorescent materials, there's also inorganic ones and organic ones. So like inorganic ones, some carbazoles and down conversion materials, they also have similar phenomena. In your opinion, what's the pros and cons of the two groups of materials?
Well, that's a very big question across the different fields. I didn't start with inorganic materials for a reason, because when I look into the biomedical applications, I really look for molecules that are either degradable or biocompatible. And I'm pretty biased that somehow organic molecules seem to be naturally either to be biodegraded or to be designed to be biodegradable. So that's the major reason I confine myself in organic, but not inorganic. For a lot of inorganic molecules, for example, the up conversion molecules, it's pretty much based on the ion as the traps or dopants to give all the optical feature. I think the key difference between organic and inorganic seem to be the light harvesting properties. Inorganic tend to have very small light absorbing cross section, and organic molecules actually can be designed to have much higher. And because you can absorb light more effectively, so your excited state carrier will be more, then the efficiency of the light utilization will be better. But for most of the applications, I think not much of the difference. And instead, inorganic molecules inorganic particles have a key feature that organic can never beat, which is the stability. Yeah.
This may also be a problem if it cannot decompose, like in the human body or the animal bodies, may become a toxic stuff. Yeah.
That's okay, which means for certain deep biomedical applications, maybe inorganic nanoparticles are not ideal. But if you, let's say, put luminescent materials on the paved road, for kind of physical-related applications, then seriously, inorganic nanoparticles is more competitive as compared to organic molecules. Yeah.
By the way, Liandu is our chair professor in the department of ABCT. Just joined us a few months only.
We met in Australia.
Yeah, any other questions, please?
Hello, if no question, let me ask. You are a colleague of Professor Liu Bing, right? I'm a colleague of Professor Liu Bing as well. I come from US. I'm Professor Sam Good. Okay, thank Professor Liu Bing's leadership in the US. I'm here actually. I'm in the robotics and the control. Okay, and I'm interested in the technology readiness. And I really like organic, decomposable, this. And if what technology is ready for me to integrate into embodied intelligence, embodied robotics, and the AI, I'm interested in that.
Well, I will not integrate the materials and embodied AIs. These two disciplines is a bit far, but I do see how materials actually can help robotics, either at the indicator or as a sensor to report the function and movement of your robotics. That's pretty much possible. So it's kind of the media, how the robotics responses to certain phenomena, and this data and results can be used to be captured, used by AI, so that you go develop your embodied AI.
Yeah, I see that one. And also the robotic can also help you to do faster, to do better, and also think.
Oh yeah, definitely. That's a different topic that I didn't talk about today. It's talking about how we should embrace AI. And I knew that actually Prof LIU just formed Academy of Artificial Intelligence, right? It's talking about how powerful when AI and robotics are coming together. I'm nervous actually to talk about this because I see in the next couple of years when AI in terms of design, molecular prediction, and robotics in terms of autonomous lab are coming into play. Many of our chemists need to think where we're going to find our job and how we can empower AI and robotics to create the next generation of the materials. That's scary though.
No, not scary. We are here to help. And actually, Professor Yang Chengguang was my former student. He is now joined the Prof LIU. Yeah, Yang Chengguang from UK.
Yeah.
Yeah.
So a key topic for the educational institution is how can we leverage AI to empower everyone, everything we do, and make sure we have a good collaboration between human and AI, right? Instead of developing state-of-the-art tools and very efficient molecular prediction, so that our chemists, our material scientists, and other peoples of different disciplines start to worry, where's our next generation of jobs? We need to bear that in mind to co-develop and make sure the AI co-scientist and the educational co-learner are able to actually create a synergy with the human to help human to be more effective.
Thank you.
Yeah.
Hey, hello, I'm KY Wong. I'm also from the Department of ABCT. So my question is there any rule for the structure of the dopant that actually can give you the longest and the strongest phosphorescence? Any rule on the structure?
Great. We start to build experience and trying to craft some, I will not say rule, but some kind of design principles, right? So now we are clear that in theory, if we have a host and the guest now is the dopant that we talk to come together to play, in theory, we stand a chance to really amplify the triplet state and stabilize them to do what we can. Means that we can manipulate them in a human way. That's for sure. We also noticed that in order for the phosphorescence to be strong, so the non-radiative decay more or less has to be minimized as much as we can. So we need all the excited state to emit light. So they cannot just vibrate and give out heat. In order for that to happen, we need crystal structures, and we need to make sure that the dopants are able to coexist in the original crystal structures. And we prefer that the new molecule will not disturb the original lattice, so that the crystal is still in the kind of the perfect format in terms of confining the molecular motion within the crystal. Because of that actually it limits what kind of dopants we can design. We need to fit into the original crystal rather than disturb it, that create a voids that will actually dissipate a lot of useful energy for light emission. We're now leveraged on the AI to study all the existing pairs and all the potential dopants with the hope that we will be able to have design guidelines and evolving with time. So as of now, we don't know exactly which dopants is kind of a magic, right? It's going to turn the stone into gold. But we do have general principle that for a lot of fluorescent molecules that people are familiar with, for example, fluorescein, for example, rhodamine, for centuries, people never thought that they're going to focus on phosphorescent emission. But now, as far as we give the right metrics, we will be able to induce the long emission from those compounds. That's quite interesting, actually, to the community. So basically, we don't need new systems to be massively produced, but we can change the existing molecules. We don't change existing molecules, but through the doping, we can change the optical properties of the molecules that we have.
By changing the structure of the molecule.
So we just treat the host molecules as the light harvester to collect the energy, and this energy will be transferred to the gas emissions through different ways. It can be through triplet. It can be through the intermediate, that is the charge transfer states. Different mechanisms, we will be able to modulate the color emission at the end. We will also be able to modulate the lifetime of the emission. And then we can build in the mechanism to show the temperature-dependent lifetime and color change. So we can actually map up a lot of new information based on the molecule that people have with a fixed lifetime, with a fixed emission. So that's what we want to do, is to give you a lot of function, but doesn't change your compound by itself, or don't recreate the materials for the country or for the world, but change the properties of all the materials that you may have. That's what we want to do.
Thank you.
We have a few questions. Sorry, we have a few questions from online.
Oh.
So being today is very popular. So by the way, so I introduce myself. This is Benga. I'm from the ABCT as well. So I'm also from Singapore. NTU. Time really flies. I have been in the Poly for about 1 year. So happy to see Bin. So the question is, how can we draw inspiration from nature to construct organic devices?
Oh, wow. I'm not an expert in this, but I knew that there's a great professor at Prof LIU. His name is Wang Zhuankai. He's doing nature-inspired materials and materials conversion into device. My understanding is that as far as you're passionate about one specific phenomenon, you really leverage on the state-of-the-art characterization techniques to understand what form that function and what is the material structure, and then you're trying to mimic and recreate using human way in order to get that function, right? And after you get your desirable function with that materials, then you think about what is the processability, how you can incorporate that materials into the device that you're interested in. So along the way, you may talk to professors in different areas of different labs, right? Some will help you on materials, some will help you on characterization, and some will help you on the device. I don't know whether you're from Prof LIU. If that, I think you just go approach PAIR, which is the great interdisciplinary platform that you will be able to find professors of all different disciplines that will help you to realize your dream and goals.
So yeah, very good. And actually today, she did not mention the other very famous field, very beautiful, so especially in biomedical, which is AI imaging and light responsive the therapy and so on and so forth. So this is the other question regarding to this. So today you introduced the iso structure induced phosphorescence, right? And people wanted to ask this how different with the AIE. Induce the luminescence or phosphorescence. What is the difference in between these?
Okay, that's a great question.
Yeah.
A very broad question that cut across two kind of literally disciplines within the broad context of the organic fluorescent materials. I have been working on AIE, which stands for aggregation-induced emission, for many, many years, and I'm still working on that. That one is a phenomenon. The phenomenon shows that when molecules that are very well dispersed in the solvent media, right? So they have the freedom actually to rotate and then to interact, so that this molecular motion or other mechanisms may dissipate the energy. So as a consequence, you don't see a strong background signal when the molecules are very well dispersed. But now once you induce aggregations, you can form nanoparticles, you can form aggregates, you can do the spin coating into the films. When molecules are come into close contact, in many cases, those molecules will actually show quenched fluorescence. But if those molecules, when they come together, that they show the aggregation-induced emission or the emission enhancement, those molecules, we will classify them into the molecules with aggregation-induced emission. All right. Now what I talk about today is more like a dopant. If you are in the organic electronics or if you're in the inorganic materials, the dopant concept is very much close to what I share today, is that you have your molecules, regardless if the AIE molecule or ACQ molecule or other molecules that you can classify. What I wanted to achieve is to understand your molecule and then adding a small fraction of the designed molecules, which today I use the isostructure doping as an example. Once these new molecules are mixed together with the molecule you have, we hope to change the optical feature of the initial materials that you have. So that's what we do today. And because we're able to change the lifetime of the molecules you have, and we can bring the fluorescence emission eventually into the phosphorescence emission with a much longer duration of the lifetime. So that is one strategy to change the light emission and light lifetime of the molecules. So they are connected, but they are quite different in terms of the molecular designs and systems.
Very good. I think still many questions, but we only have a time slot for the last one.
Sure.
So the question is, what is the structure and activity relationship between the spin, the coupling intensity, the molecular spin, the coupling intensity, and the ultralong fluorescence? What is the structure activity? Structure and activity relationship for the spin, molecular spin, orbitals, and also the super long, the fluorescence.
Well, that one is almost like a quantum chemistry. I'm not a super expert of that. So as of now, to be honest, in my lab, I don't have a quantitative data to link the spin and the lifetime yet. So I will not be able to give you a precise design, like how you design the spin so that your lifetime will be much longer or shorter. So all we have now is based on the molecular structure that we start with as a host, right? How we can design the different guests so that we can interact with the hosts to be able to modify the emission as well as the lifetime. And I would suggest you to just drop me an email. You can find my email online so that I will be able to study a bit more about your question, and maybe whenever I have an answer ready, I can email back to you to really explain how the lifetime may or may not be directly relevant to the spin that you're interested in.
Okay, I think because of time constraint and we don't want to overwhelm Professor Liu, and so it's time for us to close this Q&A section.
Thank you very much for Professor Xin chairing this session. Professor Liu, please remain on the stage. You have gave us a great lecture, so prepare this plaque just as a memory and to show our appreciation to your lecture. Okay, we like to invite Professor Yang and Professor Wang for our session, and Professor Wang to come to the stage to take a photo together. Okay, thank you very much. Please give Professor Liu another round of applause. Thank you. So I'd like also to thank all the participants to this distinguished lecture and also those online. And I wanted to express my special appreciation for those who ask questions to make this lecture even more successful. So this lecture is adjourned. Thank you again.